All right, so here we go. Let's start talking about what Isaac Newton contributed to this idea of motion and dynamics. Okay, but here's the thing: it doesn't start with Isaac Newton. It also doesn't end with Isaac Newton. It just said you'll see later that he just really generalized everything into laws of motion. Okay, now the first person that we really do focus on when we talk about motion is Aristotle. So really, prior to Galileo, right, which is around 1600, scientists and philosophers mainly, right, so the main philosopher that we will focus on is Aristotle, right? They just came up with these ideas that the quote unquote natural state of an object was to be at rest, right? Was to be not moving, okay? And so that's what Aristotle was saying, and he really came up with these two concepts, right? One is this idea of natural motion, which is what I just described, where an object wants to be at rest, okay? And then he came up with a second idea, something called violent motion, right? And so violent motion is now when objects were moving. So how did you get that object to move? You imparted a violent act to it to get it to move, right? And it did its thing, okay? But it wasn't natural, right, for this object to move, okay? So therefore, by thinking that it was natural for objects to be at rest, right, moving objects weren't in its natural state, right? Fast forward roughly 2,000 years or so, Galileo is now conducting controlled experiments. You have to remember, Aristotle was a philosopher. He did not do experiments. Okay, a lot of those Greek philosophers that came up with scientific and mathematical ideas didn't necessarily test it themselves. Okay, so Galileo conducted controlled experiments, including the object's natural state was not at rest, but is in motion or moving, right? Okay, with a constant velocity. So now we're getting this kind of conflicting view. One person saying that the natural state was at rest. The second person saying it's actually the natural state and confirmed by experiments that the natural state was to be in motion with a constant velocity, right? So according to Galileo, though, rest was part of this natural motion, but it was a special type of motion where the velocity is equal to zero. Okay, so we're starting to formulate these ideas now, right? So now we're starting to pinpoint what is actually happening in our universe. Now, it was left to Isaac Newton not necessarily to create, right, these new experiments or whatever, but what he did was he generalized the results, okay, into what we now know as his first law of motion. Okay, so again, it wasn't Newton necessarily doing this, he's just writing it down. And where did he write it down? It was in a book called Principia. Okay, that's not the full title. Principia is just kind of the shortened version. It's like the principles of the natural mathematical sciences or something along those lines. But, so he's writing this stuff down and he's generalizing all these ideas and studying these ideas of Galileo and Aristotle and other scientists and writing them down. So what he does is he says that the first law of motion states, right? So this is what he says. All objects, I'm kind of change this up a little bit. It's not exactly what he said. I'll say what he explained, what he said a little bit. So all objects will remain in their state of motion right? Unless acted upon by an external, right? There's our external idea again, outside of the system, unbalanced force, okay? So what are these states of motion? Well, they're up here, right? They're They are Aristotle's notion of rest and Galileo's notion of in motion with constant velocity. So he's taking the two concepts that were developed by Aristotle and Galileo and writing it down into a single law, that objects are going to remain in whichever state of motion they're in, whether it be at rest or moving with a constant velocity, until you do something to it. And what do you do to it? You apply an external unbalanced force, right? Remember, it has to be external. It can't be internal, because it is the external forces that change that affect the motion of the object. Okay. Now, this law does have two subheadings. Okay. The first sub kind of heading is that we know it as the law of inertia. Okay. And what happens is the definition of inertia is the tendency of an object to continue in its original state of motion. Okay. And so basically what that tells us is that objects are going to resist that change in motion unless you do something to it. Okay. This is like the coin and the index card into the cup trick. Okay. That object, that coin, is not going to move into the cup until you do something to it. And what do? You flick the card out and it drops straight down. Okay. Now, there is a physical quantity that all objects have that is a measure of inertia, and that's the object's mass. Okay. So we're going to redefine that concept of mass that you have from other science classes. The idea is that mass is the amount of matter an object has. Well, to us in physics, it's the amount of inertia that is possessed by an object. Okay. So the more mass an object has, the more inertia it has. You can even say, right, the less mass an object has, the less inertia it has. Okay. The thing is, whatever words you're using there, they have to match. They have to be the same. Okay. So if I have, and what they like to do in multiple choice questions is give you a bunch of objects that are moving or one that is not moving, and ask you which one has the greatest inertia. You're just looking for the one with the biggest mass. Okay. In fact, this is what we sometimes call inertial mass. And now there is a difference between gravitational mass and inertial mass, but we're not even going to worry about gravitational mass. We're just going to focus on inertial mass, and we're just going to call it mass. In science, the SI unit for mass, or let me put it this way, in physics, the SI unit for mass is kilograms. Okay. Now, the interesting thing is I found this out the other day, is that the US version is what is called slugs. I found that very interesting, where one slug is about 32 pounds. So just to give you an example, Mr. Londa weighs 7 slugs. Okay, it's like 6.99 slugs. And so that's just an interesting thing. It's someone I was talking with, they said, oh, it's kind of like stones in Ireland and England. I was like, yeah, it's very similar to that concept. Okay, in fact, they may actually be near the same conversion because the number of stones is roughly about that same too. Okay, so I mentioned before that it has two kind of subheadings. The first one was the law of inertia. The second one was the law of equilibrium. Okay. And so it's often called this because all the forces that we have acting on the object, they're balanced, right? So they're basically canceling each other out. Okay. Now, this leads to one of the big misconceptions, and of course, AP is going to try to harp on this misconception. They're going to try to hit you with it. Is that objects cannot be in equilibrium if they are moving. Okay. And that is a complete false statement, because there are two types of equilibrium. The first one, which we call static equilibrium, and this is the one that everybody's familiar with because that means objects are not moving, right? Okay, so with static equilibrium, the velocity is equal to 0. So one thing you can think about is bridges, buildings, or freestanding structures, right? Those are in static equilibrium because all the forces are balanced on them, and you really don't want motion. You don't want acceleration, okay? But here's where the misconception kind of gets blown up a little bit. Okay, in fact, it gets blown up here, right? So we have something that we call dynamic equilibrium. which means that the object is now moving, but with a constant velocity. Right? When we talk about the two states of motion, the two natural states, at rest, constant velocity. They're your two types of equilibrium. Okay? Now, these first law generally is more conceptual based on the test. So if we're looking at this, it says a passenger sitting in the rear of a bus claims that she was injured as the driver slammed on the brakes, causing a suitcase to come flying toward her from the front of a bus. If you were the judge in this case, what disposition would you make and explain? Okay, so I feel like I may have mistyped this because I think she is. Oh, okay. So she's on the back of the bus, right? And the suitcase is in the front of the bus. So she's claiming that the suitcase came flying back at her, right? So what happens is so if physicists can be asked to be expert witnesses on cases. Okay, it happened to a college professor of mine, and so she was in on a case for insurance, right? Basically, the lawyers were asking her, could this have happened? Okay, and so this is basically what this question is asking, right? So, what kind of disposition would you take if you're the judge? Well, first of all, you would throw this case out. Okay, so that's the thing you would do. Now, why would we throw this case out? Right, that's the answer, but why? Right, so this is kind of the explaining portion. So why are we going to throw this out? Because the object wants to keep moving, right? The suitcase wants to move. So here's our bus. I know I'm a great artist, right? Here's our suitcase. Here's our person, right? And so, what am I doing, right? And so she's saying that this suitcase, right? Her claim is that this suitcase went flying back at her, right? But in actuality, which way does the suitcase want to keep moving? It actually wants to keep moving forward, okay? So when you slam on the brakes, you're going forward. Think about it this way. If you're ever in a car and you slam on the brakes, what does your head do? Your head doesn't necessarily slam back right away. What does it do? It kind of leans forward because it wants to keep moving, right? So the suitcase, right, wants to move forward based on its inertia. Right, because of this concept of inertia. Right, not backwards. Now, if this was done when the bus was accelerating, then yes, the suitcase would have caused the damage, right? So this is if we were accelerating, right, forward. So we'd have a positive acceleration, right? But here we have a negative acceleration because we're slowing down, and the suitcase wants to keep moving forward, right, towards the front of the bus, not towards the back of the bus. So if I was a judge in this case, I'm throwing this case out because the woman or the person has no claim. The passenger has no claim to say that, yeah, that suitcase is what caused, whatever her, injuries were. All right. So that's his first law. So think about law of inertia, law of equilibrium. Okay. Then next video, we're going to focus on the third law. I know it seems weird, we're skipping the second law, but the second law is going to be its own topic because this is where we're going to start applying mathematical equations and mathematical formulas.